Greetings everyone, welcome to Side A, Side B. In this video, we're going to be doing some background work to solve another problem of divisibility, a more challenging one. We'll pose the problem in another video. Apparently, Carl Friedrich Gauss, while in elementary school, found a way to sum a large series of numbers. He noticed the first and last terms made a sum, and there were n of those sums. So the summation formula that followed was the average times n terms. Does that mean he was an average student? Overall, though, his work speaks for itself. We're going to be doing a proof of the general formula for an arithmetic series. If we need it, it'll be there to reference. And then we'll check our work doing a difference equation using the delta notation. So we're good to go. First of all, we're going to be looking at an arithmetic sequence. An arithmetic sequence that we're going to be talking about. A list of numbers. And what really defines an arithmetic sequence, it has a common difference. In this video, it's going to be a part of some background knowledge to help solve a problem. If it's a list of numbers, it follows that it's a list of integers. And integers, it's a number. Some people call it the whole number. It has no fractions. Like, for example, the even numbers, the following even numbers, 4, 6, 8, and 10 is a sequence. So what's the common difference? To find out the common difference of those numbers, those integers, all we do is find the difference between each term. Pretty straightforward. 6 take away 4, 8 take away 6, 10 take away 8. We just have a list of 2. So the common difference is 2. That seems pretty straightforward. So those differences make a new sequence. In our second example, we have the odd integer sequence. That seems straightforward again. All we do is find the difference between each term. 3 take away 1, 5 take away 3, and so on. Makes a difference of 2. So those differences makes another sequence. But what if we want to find the sum of that sequence? Let's formalize that sequence and name it B sub n. So in order to sum those integers of our new sequence, we need a series. And a series is a sum of all those integers of the sequence. So just to differentiate, we'll call this B sub I. And that's going to be the name of our series. If we have just 5 terms, we can sum those terms in our head. What if there's 1,000 terms? What if there's 100,000 terms that we want to sum up? We need a different technique other than doing mental math. So there's 5 terms there. So notice the first and last term, 9 and 1 equals 10. And the 2 terms equidistant from each other are 3 and 7. And the middle term is 5. So there's 4 terms that are equidistant of each other. 1 and 9 and 3 and 7. So let's use that, see what we can come up with to finding a formula that can sum an nth amount of terms. So what we do, change the order of the series. Now we have 5 sums of 10. 9 plus 1, 3 plus 1, and so on. 3 plus 7. And then 5 plus 5, 7 plus 3, 9 plus 1. That gives us 5 tens. And that equals 50. However, our series equals 25. So what gives? Notice though, we sum the series, and that series just equals 2b sub I. So in order to solve for b sub I, we need to carry over the 2. And the final answer is 25, and that's the answer that we want. But there's one thing to notice, is that the first and last term equals 10. And there's 5 of them. It's all over 2. So all we're doing is finding the arithmetic average. There's the idea of a general formula for the arithmetic series, which is I times b sub 1 plus b sub 5 all over 2. So we propose the general formula for an arithmetic series is I times the first term plus the last term, b sub I, all over 2. It's finding the average of the first and last term. And then timesing it by I times. Make sense? So we propose that the general formula for an arithmetic series is I times b sub 1 plus b sub I all over 2. So let's take a look at the general formula for an arithmetic sequence. For example, like in the first sequence, if we want the first term, if we want to evaluate the first term, we have to, n has to be 0. But in the second equation, it's the first term is b sub 1 and needs to be a 1 to make that a 0. This general formula for an arithmetic sequence, both of these equations will work. Both of these equations are essentially saying the same thing. But me personally, if I see a b sub 0, it's telling me that the first term for n is going to be 0. In the second equation, the first term is b sub 1, so that's telling me 1, and that's going to make that term go to 0. So that general formula is going to make a sequence. We wrote it in 4 terms. Often it's written in 5 terms. And D equals difference. And as you can see, it's a list of terms in its general form. And if you notice in the general formula for a sequence, D is 1 less than n times. First term is b, second term is b plus d, third term is b plus 2d, so it's 1 less than n times. So we index n, take away 1. So we're using equation 2, but we could have easily used equation 1 as well. So what if we want to sum all those terms. Again, we put it into a series. We're renaming this one capital B sub n equals the following series. How did we sum that series? Well, just recall the short demonstration we did. All we do is make a duplicate of that series and then rearrange the order. And then we sum those two series. Reordering our series, so summing them. After reordering the series, we get the resulting series below, and it's just a matter of summing them up. The first one, we get 2b sub 1 plus n take away 1 times d. Second one, the first term is the same, n take away 2. If we have one more term than n take away 2, we have n take away 2 plus 1, which makes n minus 1. So that term goes to n take away 1 times d. Nice. And the third term, same thing. What if we have two terms more than n minus 3? We get the same thing, n minus 1 times d. Nice. So did you see a pattern emerge? All those terms equal each other. 1, 2, 3, and 4. And there are n of them. If there's n of them, we can simplify. All those terms get compacted into the following equation. And to solve for b, capital B sub n, we do the same thing as in our demonstration. Those two, we divide both sides by 2. It's just a canceling operation on the left. So there's the general formula for an arithmetic series. In our first demonstration, we posed b sub n equaled n times b sub 1 plus b sub n all over 2, finding the average and then timesing the average by n. So let's rearrange the general formula for the series. And 2 b sub 1 is just b sub 1 plus b sub 1. And take a look. Notice the first term is b sub 1 in our series, and the last term also equals the last term in our series. First term, b sub 1. The last term, b sub 1 plus n times 1 times d. So indeed, that checks out. Are you with me so far? Let's test out that formula. Let's see if we can find the general formula for the odd integer series. To do that, we need the general formula for the sequence. In the first term, if we name it a sub n, the first term is going to be 1, a sub 0, and the difference is going to be 2. If we use that type of formula, we have to use 0 as our first term. As we have to, n has to be 0. If you want to write it that way, if you want to evaluate our first term, and it's going to have to be 0. That's for the sequence. Now let's look for the general formula for the odd arithmetic series. And all we do is plug in the first term, which is going to be 1 plus 1 plus n take away 1 times 2. 2 is the difference, obviously, all over 2. And what does that leave us? It leaves us with the following formula. 2 times n squared all over 2, and the 2's just cancel, which just leaves n squared. And that's the general formula for the odd arithmetic series. Is that true? Let's check it out. Let's see if that's true. For example, just consider any series. If we want to find the general formula for the sequence, all we have to do is find the difference. If we consider a series that's one term more, if we can duplicate a series and then we can do a different operation, we can find the difference. If we can make a duplicate of the series and then we subtract the series, well, it's going to be 0. But if one series has one more term than the other series, and then if we subtract them, we're just going to be left with one term. Make sense? If we subtract 2 similar series, and then one series is one more term more than the first series, then what are we going to get left over? One term. Nice. And we're left with the general formula for the arithmetic odd integer sequence. And that's how we're going to check if our answer is correct. So just consider the following notation. Delta denotes a difference. And sometimes that notation, delta, can denote a change. So what do we want to find? We want to find if delta denotes a difference, then so the change of b sub n equals n plus 1 squared minus n squared, which just means n plus 1 squared is one term more than n squared, which gives n plus 1 times n plus 1 minus n squared. If we FOIL out n plus 1 squared, and that simplifies to, and canceling terms, bringing all the like terms together. Take a look. That's what we were aiming for. Final answer is 2n plus 1, and that means everything checks out. We're left with the general formula for the odd integer sequence. Nice. Well, we went full on average using the Gauss method. Whatever the mean is, it's been an absolute pleasure to bring this video for you. See you in the next one.